So last time we discussed how to deal with, also how to find the different derivatives of a multivariable function, especially when your function is defined from 2 dimensions to a 1 dimension. So 2 variable real value function. So the idea was if your function, so last time, our idea of differentiation was a function, so which is defined on open set in 2 dimensions to 1 dimension, and is differentiable at a point A. This is defined to be if and only if h is tending to 0 and f a plus h minus f of a minus r a at h by a h is tending to 0. So, and this was what? This was a linear function from R2 to R. And it turns out to be that LA is a function whose components are just a partial derivatives of f with respect to x and okay. All right. So, well, that was basically the idea. So, the derivative. So, well, this guy LA, so which is turns out to be nothing but a linear function from R to R. This is a derivative, and derivative. This function is actually approximating LAH is approximating FA plus H minus FA. So from now on, so whenever, okay, suppose that somebody's asking, what is the derivative? Then the answer is derivative is a linear function that best approximates f of a plus h minus f of. So that means, well, therefore, by the definition of derivative, it looks like the derivative is developed for a linear approximation of possibly non-linear. And we're going to extend this discussion towards much more general class of functions. All right. So today, we're about to turn to the function. Okay, this is not a real values function anymore. So this is a function from Rn to Rm, and say that this guy is defined on some open set U containing a point A. And we say the function is differentiable if this guy, well, fa plus h minus f of a can be well approximated by a linear function La in the sense that this guy is tending to 0 as the length of the vector h is tending to 0. Okay, so like my previous lecture. So what you're gonna do for today's lecture is we wanna find this linear function Ra. Okay, what is Ra? Well, for now, let us suppose that our function f is differentiable at point A. differentiating fa plus h minus f of a, but fa plus h minus f of a, this function is a function defined on Rn to Rm. Therefore, this function must have the same domain and same codomain, just like this guy. So in other words, LA is a linear function from Rn to Rm. Right? And this is linear. Yeah. And you should remember that every such a linear function can be represented by a matrix of whose dimension is m by n matrix. Yeah, it should be represented by m row. Should be represented by a matrix that has a m rows and n columns. Right. Okay. So speaking of which, so that means LA, well, here H. Well, and H is, well, as always, this Y is considered as a column vector, and n-dimensional column vector. So LA of H can be written like this. So this is LA, and this is H, right? Well, as you can see from this picture, so I have M rows, right, and N columns. Okay, so provided that my function is differentiable at point A, and today we will try to look for what these numbers are. These are also very mysterious numbers, but these numbers are also very much something to do with the so-called partial derivatives. Okay. All right. Well, in order to find these numbers, these entries of this matrix LA, then first I want to write down this function, my original function, in terms of the component. Okay, so we write my function f, f1 and f2, f m. Why? Because this is this guy is a m-dimensional vector, right? Therefore, this function f must consist of these m component functions, right? And each of these components, from small f1 to small fm, they are all real values. These guys, these components, they are all real values functions defined on Rn, right? So, I mean, in other words, these guys, these component functions are real values, n-dimensional real values functions, right? And, sorry, n-variable real values functions. Okay, now we assume that f is differentiable at point A. And in component, yeah, I would say A1, A2, and AN. Because A is a point in n-dimensional space, so therefore, so these are just n components, and so these are just n numbers, and they are the component of the point A. Okay, now, and so f is differentiable means, by definition, f is differentiable a plus h minus fa minus la of h and everything. And this guy should tend to 0. So, and well, as before, so we are talking about the case when the length of H is tending to 0. So this vector H is an n-dimensional vector, right? So this vector H lies in this n-dimensional space from so this is x1, this is x2, and this is xn. So this is the n-dimensional space where this vector H lives in. And and the limit of this guy exists and this guy equals to 0 means, well, the vector H is tending to the origin, right? So this is what it means. This is what limit H goes to 0. So vector H is tending to 0, but there are so many infinitely many different ways that H is tending to 0. Well, H may tend to 0 following this route or following that route or following this crazy spiral route whatsoever. But the point is, well, even so, the limit of this guy exists and equals to 0 means no matter which route you choose, but this limit should exist and this number must be 0, right? So in this case, well, I will try to follow this route. Along this route, along with this x1 axis. So we follow so H1. Well, there's no H2 because, well, since we are following this route on this x1 axis, so we are about to consider this route. Okay, so, well, by replacing this H by this H by this guy, yeah, these are n-dimensional vector, and H1 is tending to 0 means that we are about to consider the route along with this x1 axis. Okay, but however, in this case, well, the limit should be also 0, right? All right, so since we are slightly running behind of the schedule, okay, so this, so this first equation, so this is simply the definition of being differentiable at point A, right? Okay, but here I am replacing this A by this guy, well, this component, right? And this H by this guy. So this is sum of two vectors. So A plus H would be like this, right? A1 plus H1, and the other components, they're just like same as A. So A2, all the way to AN. Minus F of A. And this is F, and this is A. Now minus LA times H, LA of H. And this is LA, and this is H1, then the 0, 0, 0. And, well, and moreover, this denominator, which is the length of H, it can be simply replaced by this absolute value of this small h1, right? And this limit should be, again, 0, right? Because we are assuming that this is differentiable, right? So even if we are following this route, the limit must be also 0. All right, okay. Okay, now what? Now, this line of equation and this line of equation, they are almost identical, but here I am replacing this guy by this weird symbol. And hey, how did I get this? This is this. Well, this is LA, and I told you this function, this error, this linear function can be represented by this matrix. And I am plugging in h1 and 0, 0, 0. So suppose that this they all just, well, this is LA, and but this time h1 and 0, 0, 0, other except for the first component, then all the other component equals to 0. If you plug in this guy here, then this guy times this, and 0 times that, 0 times that, da, 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 and if you add them all together, then the first component will be just A11 times H1, and the second component would be H12 times H1, and the last component would be AM1 times H1, right? Right? And so because of the reason, yeah, I am writing it. So I have this expression. So this is simply, well, simply put, this is the first column of this matrix multiplied by H1, right? Okay. So we have M component over here, but well, this guy and that guy, they are also vectors in m-dimensional space, and this function large F is consisting of these small m component functions, right? So this guy is tending to 0. Well, the numerator is the just length of the n vectors, and this guy is tending to 0 means, well, now writing everything in terms of the component functions of F, the first component, the i's component of this guy is this, right? And i's component of this guy is this, and the i's component of this last one is I1 times H1, right? We are just taking the i's component of each of these vectors. And this guy tending to 0 means that each of the components should also tends to 0 as H1 is tending to, right? So we have such an I equation. Well, so even though I have written just I, but this is not just a single equation. These are collection of m such equations. If this guy is tending to 0, then if and only if all these m limits also must be 0. Okay. Last expression looks very familiar to us. This is just simply a derivative of the real value function. So in other words, simply put, well, so this expression is mathematically equivalent to, well, H1 over here on the bottom and top. So they just cancel out each other. And side to the other side, then we end up with that. Okay. Okay, good. So we have, and so, well, again, this is not just a single equation, but these equations are true for all i's from 1 to m. So they are m such a limit, m limit. Okay, all right. Now, this last expression looks very much like just a ordinary differentiation in freshman calculus, right? In this case, well, the first component is now being differentiated, and all the other components, they are just remains the same, right? Carries over. So this is what we call the partial derivative of function fi with respect to the first variable. So this number is called the partial of f. This is the partial derivative of the i's component function divide by, well, not divide by, over first component. So i's partial derivative. So getting differentiated with respect to the first variable and evaluated at point A. Sometimes we just write down like fi and x1 and evaluate it at. So these are just notations, and we say this is the partial derivative of fi with respect to x. Okay, good. So, So now this gives us some insight on this linear function. Well, you have to remember at the very beginning, so we wanted to find what this matrix is. And it turns out to be the entries in the first column of this matrix, they are obtained by taking the partial, sorry. Yeah, so the entries in the first column of this matrix, they are obtained by taking the partial derivatives of this component function of f with respect to the first variable, right? And well, as I told you, so taking the partial derivative is not a big deal because, well, because of this definition, so the computation of partial derivative is exactly precisely the same as the computation of ordinary derivative as we did in the question. So that means as long as you can do the ordinary derivative, then you can still do the partial derivative. And do the partial derivative and plug in that x point that and evaluate at the point A, then you can get all these numbers in the first column of this matrix. What about the second and all the other columns? They are the same thing. Well, you can do the same thing. Well, here we are following this route, but if we follow this route, then if you follow the second route along with this x2 component, x2 axis, then these numbers are also easily obtained. And if you follow this route, you can also get all these numbers also easily. So generally speaking, any random component of the matrix L is the partial derivative of i's component with respect to the x and evaluate the partial derivative at point. Then this is going to be the entry of the matrix. Okay. So, oh, yeah. So this is the conclusion of today's lecture. Yeah. Well, this is yeah. I know only 30 minutes has been touched, but this is the conclusion of today's lecture. Well, so the definition of derivative involves this linear function. So being able to find such a linear function, well, turns out to be not a big deal as long as your function is differentiable at the point. Well, that is, the entries in the i's law and j's component is obtained by you take the i's component function of original function f, and you take the partial derivative of that function with respect to the j's variable and evaluate this function at point A. Then that is how you get this entry. So once you get all these numbers, so basically, therefore, in order to find all these numbers, then you have to do n times n many such computations. But well, the point is, they are just not a big deal. They're just tedious computation. Once you can do that, then you can find this. So we write this one. If this matrix is denoted by df of A. So our textbook says this is the matrix derivative of function f at point. So this is the derivative. Okay, then now why is this so important? Because, okay, so this is the definition of the limit. So suppose that we were able to find this matrix, then, well, since this guy is tending to 0 means that the numerator should also tend to 0, right? So f a plus h minus f of a, they are super close, especially when the length of h is equals to h is very small. So that means if h is very small vector, well, if the length of h is very small enough, then this function is very well approximated by this linear function. Okay, so this is the derivative. Well, okay, so from now on, suppose that someone else is asking you a question like, okay, hey, do you know what the derivative is? Then your answer is supposed to be, aha, derivative is a linear function that approximates function at a plus h. I really like this slogan. This slogan describes both all those definitions of the limit and all those definitions of the derivative, from the high school definition to the university definition. Derivative is, well, so therefore, derivative is mainly used when you want to linearly approximate any function. Derivative is for the linear function. So therefore, because by its own nature, the derivative is linear. Derivative is a linear. So important. So which best is okay. So okay. So this last expression can be also written as a plus h can be approximated by fa plus la times h. And okay, now let me change our notation a little bit. I want to put a plus h to be x, then fx is then fa plus la, and a plus h is x, therefore h is x minus a, right? So, and this right hand side of this equation, this approximation, is called the linear approximation of f. So this is what we call the linear. Remember, if f is a single variable function, if f is a function from R1 to R1, then linear approximation turns out to be nothing but the equation notation. All right. Small exercise. Just to check if you're on the right track. Suppose that we have such a function, x squared plus y squared and x minus y cubed. This is highly nonlinear function. And I want to find the matrix, I want to find the derivative of function f at point 1 comma minus 2. Do you think you can find it? Well, first, let us consider the domain and dimension of the domain. The dimension of the domain is 2 dimensions, right? Domain is 2 dimensions and codomain is 3 dimensions. Therefore, this matrix derivative should be represented by narrow matrix, which has 3 rows and 2 columns. So df xy, which is partial f1 over and partial x and f1 y f2 x f2 y and f3 x and f3 y. Right? But well, here this is f1 and this is f2 and this is f3. So if you take the partial derivative of the first component function with x, and this is going to be 2x because we are taking the partial derivative with respect to x, and the f1 partial y, it should be 2y, and this is f2, so partial f2 partial x is 1 and 0 and 0 and minus 3 times y squared. Okay. Okay. All right. So, and this is the general matrix derivative, but we are supposed to find the matrix derivative at this very special point. So, and all you have to do is just plug in these points into these partial derivatives, so which is 2 minus 4, 1, 0, and 0, which is 12, I guess, and minus 12. Yeah. So this is the matrix derivative. Okay. All right. Okay. Okay. So when you're studying calculus, yeah, I always try to emphasize the geometric intuitions to work in the. Okay. So. Well, suppose that we have some function. Yeah, in this case, the dimension of domain is 2 dimensions, and dimension of codomain is also again 2 dimensions, right? And say that this is my point A. This is A, and say that this is my point f of A. Okay, now we say that we are at this point. Now, what I want to do is I want to approximate the function value at this point. Well, suppose that I have moved to the direction of the positive x-axis by epsilon. Suppose that I have moved this much. Then what do you think of your function value at this point? Well, say if you then this function value at this point can be approximated by this point plus LA of epsilon comma 0, which should be this point. Well, this is the precise function value, and this is your approximation, right? So this is how you approximate your function. So this and so now say that I want to approximate our function value at this point, and you have moved to the positive y in the direction with the positive y-axis by epsilon. Then, in order to approximate the function value at this point, then what you're going to do is f of a plus LA times 0 comma epsilon, which should be this point. This is your approximation, and this is the true precise value, and this is the approximation. So your precise value and your approximation is deviated this much. So yeah, I can also give you the geometric intuition. Right? So this is how usually matrix derivative, especially on the approximation. Okay, good. And here's a very interesting notion. Now consider this very special case when n is n. So in other words, the dimension of the domain and dimension of the codomain, they are the same. So from n dimension to n dimension. In this case, in this very special case, we can define a number which is called the Jacobian of f. So what is this number? So this is easy. So if n equals to m, then matrix derivative of f at this point should be a square matrix, right? Since the dimension of domain and codomain, they coincide each other. So in this case, your matrix derivative must be a square matrix. And well, then, and for any square matrix, then you can define a determinant. The matrix is the determinant. And so if you take the determinant of the square matrix, the determinant of the matrix derivative, then this number is defined to be the Jacobian of f at x. This is the Jacobian. Okay, so what is the geometry intuition of the Jacobian? Yeah. Well, you should remember, well, if you have a linear function, so this is a linear function from R2 to R2, and say that you have such a function. The point x comma y is now being mapped to this matrix times xy. So in other words, this matrix, this linear function is represented by this 2x2 matrix, and the point x is being mapped to the a times x plus b times y, and point y is being mapped to the c times x plus d times y. Suppose that you have such a function. Then you can, then what is the geometric meaning of this determinant of this matrix? The geometric meaning is this. Well, suppose that you have a unit square on your domain. Then what do you think is the image of this unit square? The image of this unit square is this parallelogram, right? Why? Because sorry, yeah, I messed up. This is E1 and this is E2. Well, because the image of this guy, which is 1, 0, is A comma C. If you plug in 1 comma 0 here, then A, C, you're going to get A and C. So image of this guy would be this, and image of the second standard unit vector must be this. So therefore, every other point obtained by some, well, so so all these vectors that lies in this square can be written as some S times S1 plus T times E2, so S times E1 plus T times E2, such that S plus T equals to is between always 0 and 1. So if you consider this equation, then I guess you can easily be convinced that the image of this unit square is going to be this parallelogram. And I say determinant of this matrix is, well, it's going to be the area of this parallelogram, right? So what does it mean? I say the determinant of this linear function is a stretching factor. Suppose that you have some geometric object that has a unit area, and geometric object in your domain is now being mapped to this much geometric object, and determinant of L gives us the ratio between the unit area object, and the image of that. So if this guy is greater than 1, then this image, if this area has been stretched. But if this number is less than 1, then this area, this image of this unit square is now has been shrunk. Okay. So this is the geometric meaning of determinant of L. And in this case, well, suppose that this green shaded region is being mapped to this guy, right? But, well, if this guy and this guy, if they are fine enough, then, well, we can approximate the image of this guy is almost like the image of the parallelogram spanned by these two blue vectors. Okay. And what do you think is the determinant of this determinant of this matrix derivative? It's going to be a stretching factor, but not a global stretching factor, but a local stretching factor. So that means, so if this number is greater than 1, suppose that this number is 7, then, well, when you're very close to this point, then unit area, the geometry object that has a unit area has been stretched to another geometric object in this codomain, and this stretching factor is by multiplication by 7. Okay. And if this number is less than 1, then instead of stretching now, then this guy, this unit object in the domain has been shrinked in your codomain. And what if this number is negative? Suppose that this number is negative, say, -3. In that case, the area has been stretched by a factor of 3, but the orientation now is reversed. So, therefore, if this is the first vector and if this is the second vector, then it has been shrunk. So order has been flipped. So this is first, this is first and this second. And yeah, right. You know what I mean. So orientation has been changed. So so the Jacobian is just a local stretching factor. So if Jacobian, so computation of Jacobian gives us the idea how much the region or the area has been shrinking rate or expanding rate of your function at the given point. Okay, good. Okay. Oh, yeah. Some special cases. Well, suppose that we have such a function. Well, I'm going to name it by x, and this is function from R to Rn. the matrix derivative of this guy, this function, since it is, well, its dimension of the domain is one dimension. So yeah, I'll just say put dx of t. Then this guy, well, say that x of t is consisting of small x t, small x2 t, small x n t. Right? So say that these are the components of your function x, then its matrix derivative is dx1 dt dxn dt. So this would be your matrix derivative. And can I impose this matrix derivative any differently? Yeah. So I can say this is the velocity vector of the curve. Why? Because in this case, I told you that this such a function can be considered as a parametrization of the curve. Right? The image of this function is a curve, and the function is considered to be considered as a parametrization of the given curve. So in other words, this function has an information of how you travel on this given. And this matrix derivative turns out to be the velocity at point. So therefore, from time to time, I'm going to call this guy as a velocity vector. Because if you have a component and you differentiate each of these components, then this newly obtained vector should be the velocity vector, which is tangent to the original curve, right? And number 2. Now, let us consider the opposite. This time, we have a real values function on n dimensions from Rn to R. So in this case, this function f only has one single component, right? So then its matrix derivative df at point A. This time, this is a row vector. So partial f, partial x1 at A, partial f, partial x2 at A, partial f, partial xn at A. Just like this. And this vector is usually denoted by like this. Yeah, this is just merely nothing but change of notation from row vector to usual vector. And well, this guy can be considered as a gradient vector, as a vector field. Why is that? Yeah, this is not a vector field. This is just single vector, right? Because each of these components are the function. But if you get rid of, well, since the choice of this point A is arbitrary, that means, well, so therefore we can consider this guy as, for any given point in your domain, you can assign a vector. So this one, in this sense, we can consider this guy as a vector field. And this vector field is so special, so we gave this guy a name. So this guy is called the gradient vector field of F. And denoted by the symbol, this triangular shape means the nabla of f at, so this is the gradient. This is an exercise given in our textbook. Which is x squared times sine yz. And find this gradient vector. Find the gradient vector field. Gradient vector field of f. Okay, but this will be also doable because, well, gradient vector field is the first component of the gradient vector is obtained by taking the partial derivative of function with respect to the first variable, so which is 2x sine yz. And the second component is given by taking the partial derivative with respect to the second variable, which is y. So x squared just carries over, but z and cosine yz. And for the last component, so x squared times y times cosine yz. So this is going to be your gradient vector of u. So this is easy. It's just regular differentiation. Then, so you can easily get the gradient vector field. Okay, so before I end this section, so I would like to introduce two important result. One important result, not two. Let's go. So continuously differentiable. What does it mean? You have a function f from Rn to Rm. Then, well, in this case, the its derivative, which is just m by n matrix, then it has m times n many different partial derivatives, right? And, well, suppose that all such a partial derivatives, they are continuous functions on U. Then, so if all these components of the matrix derivatives are continuous functions, then we say the function is continuously differentiable. And continuously differentiable function is called a C1. So in other words, so that is, well, so this is your matrix Ra, and if all these partial derivatives are all continuous on given domain, then we say the function is continuously differentiable. And there is also a good news. If your function is continuously differentiable, then your function f is automatically differentiable at any point on the domain. So this is we are not going to prove. So let us take this. But anyway, but from now on, almost all functions that we are going to encounter in this course will be assumed a continuously differentiable. So that means from now on, all these functions going to, so unless otherwise specified, so we are going to deal with all differential functions. Okay, so but 우리 미적분학 코스인데 미분이 불가능한 함수에 대해서 다루면 돼요. 이제부터는 대부분의 함수들은 이제 C1이라고 가정하고 있습니다. Okay. school student, and remember when we were first introduced to the differential function, our first, so we have been often told that the derivative is a slope of the tangent. The derivative is, by its own nature, derivative is very closely related to the slope of tangent line. And we have a very similar analogy for very special kind of function. What? Because, the derivative is a slope of tangent line. So this is also acceptable because derivative is nothing but a linear function that best approximates f(a) plus h minus f. But in case when your function is from R2 to R, then we have very similar analogy. If f is a two variable real valued function, and suppose that this guy is differentiable at point A, comma B, then hey, what is the linear? And this is the linear approximation. LFA plus LA minus, okay, so F A comma B plus L A comma B of X minus A comma Y minus B. This is the linear approximation of F at AB, and we're going to call this guy, and A comma B, it just carries over, but this linear function, this is the derivative, and in this case, the derivative is fxab. This is partial derivative of f with respect to x, evaluated at the point, and the another component is fyab, and here I'm using the matrix notation, and y. And this is B, B, X minus A plus Fy AB and Y minus. So since this is a linear approximation, so I'm going to call this guy L of X comma Y. Okay. And this approximates fxy, right? Yeah, this is the linear approximation. But today, okay, now let us focus on this one. Little L, this is again a function from R2 to R, real value, two variable real value. And so how this guy related to our original function? This is the point. I want to discuss this stuff. Okay. 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 Why we are so interested in this function from R2 to R? The reason is this function, the graph of this function can be represented by a surface embedded in R3, right? So suppose that this is the graph. So this is a part of the graph of this function, z equals to f of xy. Okay, and this is an xy plane. Then this xy plane should be also understood as a domain of this function f. And the z coordinate is the function value at this point. Right? This is what graph is. And if this is the point A comma B, and there must be a corresponding point on this point on the surface surface graph, the graph surface. So this is A comma B comma f of A comma B. So this is the corresponding point. Now, what I want to do is this. I want to draw a straight line passing through on this xy plane. I want to draw a straight line which is parallel to the x-axis and passing through A comma B. And this is a curve. Well, there must be the corresponding image on this graph surface, right? Which would be this red line. This is a curve on this. This is curve on this surface. And again, I want to consider another straight line passing through this point AB, and which is parallel to y-axis. And this line also must have a corresponding curve on this surface, graph surface, right? So we can consider these two curves. And yeah, now things are getting interesting here. Now, so this is a curve. This is the surface, and suppose that I had a cross section of the surface passing through this point, AB and FAB, and cross section taken by another plane that is parallel to XB plane. Then this red line should be the cross section obtained in this way, right? And what do you think is the slope at this point? 이 포인트에서 기울기가 slope at this point, well, considering this curve as a two-dimensional graph in this cross-section, then the slope at this point would be precisely fx at this. Right? Likewise, say that I have taken cross-section of this surface this time around, another plane that is parallel to YZ plane, and passing through this point. Then such a cross section would be this red curve. And if you consider this red curve on YZ plane, then the slope at this point of this curve would be precisely FYAB. Right? Okay, now great. Okay, then now I want to consider this vector. Well, this is a curve in three dimensions, and this velocity vector over here would be 1, 0, fxab. Why? Because this curve can be parameterized by T, B, F, T, B, right? This curve can be parameterized by this way. And if you take its velocity vector, it's going to be 1, 0, fx. Okay. Likewise, this another blue vector, which is tangent to this point, tangent to this curve, is going to be 0 and 1 and fy. So these are two tangent vectors tangent to this point. Okay. Yeah. Now things are really interesting from now. Now you consider not a velocity vector, not a tangent vector, but the tangent plane, which is tangent to this graph surface at this point. And the tangent plane must contain these two vectors. Right? Okay, good. So the tangent plane must contain these two vectors. Therefore, okay, so we know that tangent, so we want to consider the tangent plane, tangent to this graph surface at this point. And in order to describe any given third plane in 3 dimensions, then all we need is the coordinate of the point and the normal direction, right? And what do you think is the normal direction of this tangent plane? The normal direction can be easily obtained by taking cross product of these two vectors. If you take the cross product, then that is going to give us the normal direction of this tangent plane. Okay? All right, good. So the normal direction of the tangent curve, tangent plane to the graph surface at A, B, F, A, B is 1, 0, F, X, A, B cross product with 0, 1, F, Y, A, B. This is, yeah. Now we have to do the cross product. I, J, K, 1, 0, F, X, A, B, and 0, 1, F, Y, A, B. So this is minus Fx AB and minus Fy AB and 1. Right? So this is the normal direction, right? Okay, now we are ready to find out the equation of a tangent plane at this point. So the equation of the tangent plane is minus Fx AB. Sorry, yeah, I just realized I just ran out of it. Sorry about that. And x minus plane. So we are talking about the tangent plane, which is passing through this point. So x minus a, and this is the second y coordinate of the normal direction times y minus b, and plus 1 times z minus f of ab equals to 0. So this is the equation of the tangent. Now, I want to solve this equation for variable z. Then z is fab plus fx a b minus x minus a plus fy ab y minus b. Okay. Now I want you to compare this guy with this small l. They are exactly the same thing, right? So this is L, X, Y. Okay, so this is the lesson. So, well, if you have, suppose that you have the function from R2 to R, and the linear approximation at any given point is equation of not tangent line, is not equation of tangent, but equation of the tangent. All right, see you next.